Hey y'all, today we are going to make a terrain generation tool in C++. Let's do it. So, the plan, we're going to create some kind of viewport, and I want to do it in OpenGL, I think, just because it's a library I'm familiar with, it's cross-platform. So, you know what, let's just go ahead and get started with that.
So the first thing I do whenever I'm working with OpenGL is I immediately abstract everything away, just because I don't like doing raw OpenGL calls inside of my code base, because I think it just kind of pollutes the code, makes it look ugly. So instead I'm just going to create classes for my vertex buffer, index buffer, vertex array objects. Pretty straightforward class design where we're really just binding buffers, generating, setting the layouts for the buffers. And of course, they should have some sort of ID system so I can easily refer to each buffer if I need to bind or unbind that buffer somewhere in my code. Yeah, it's also worth noting that we're going to be using GL dynamic draw for these buffers because, as you might guess, we're dealing with a mesh that's going to be updated, right? The buffer and the actual buffer data is going to be changing dynamically as the user sort of adjusts the parameters to make the mesh look different. And so what I can do is have my own vertex buffer layout class, and I can sort of push layouts that are specific to whatever that buffer needs. In this case, we're really only dealing with floats, right? We're dealing with positions and normal data, and that should be essentially triplets of floats. So here I'm just sort of abstracting that away so I can easily, in my code somewhere, just push a layout for floats, and then I'm done with that. I don't have to deal with that vertex attribute anymore. It's worth noting that this is not going to be an OpenGL tutorial, by the way. There are plenty of resources online where you can learn this stuff. This project is more so focused on sort of how I'm manipulating the data within the buffers. And so then in my vertex array class, I have this VBO count variable, which is just going to keep track of whichever vertex array object I'm currently bound to. Then in my main function, I'm going to insert some boilerplate, hard code in some vertices with their corresponding indices, and then I'm just going to draw elements, make sure we get that triangle drawn on the screen. That's sort of the hello world equivalent of OpenGL. And there it is. All right, now that that's taken care of, we need to talk about height maps. And a height map is actually not that difficult to conceptualize. Essentially what we're doing is we're taking x and y coordinates, and then for each sort of coordinate, we're mapping it to some value 0 to 1. So that's our height value. And the way you can think of a height map is in some sort of image format. Typically, that's how it's represented. And I'll throw up something that'll give you an idea of what I'm talking about. And so we're saying for each xy coordinate, assign it to a height value. So then, of course, in our visualization and our viewport, when we construct this mesh, we can represent that height map as the z value or the z component of each one of the vertices of our mesh. And so the first thing we need to do, right, is construct this mesh. And you see I've sort of drawn this grid here, and you can imagine those sort of vertices extending out into the x and y coordinate to whatever sort of resolution we want. And then after we've sort of set the positions, we need to, of course, draw the triangles. We're going to compose these planes that are going to connect the adjacent vertices per grid cell, you could say. And so that's just going to be the first thing we take care of, is constructing the grid and then constructing those triangles. All right, so this is our code so far. A couple things to note. First of all, we have to remember that OpenGL is only going to read a buffer that is one-dimensional, right? So all of our positions and indices have to be stored in a one-dimensional array. And so what we're doing here is we're converting the x and y coordinates inside of this nested for loop into its corresponding one-dimensional index. That's what this formula y times resolution plus x means. And so then we can resolve which vertex we're on using that formula. And you see we do that when we actually get the indices for each vertex to construct the triangles. These correspond to the first triangle. So you can imagine this is the first vertex, upper left, and then right, and then lower left. And so this will give us two triangles for each vertex. And then of course, we're keeping track of our triangle count. And let's run this and see what happens. So it looks wrong. And let's talk about why that is. All right, so here's our current scene so far. We have our camera sort of offset from the origin, and then we have our origin at 0, 0, 0. So what's happening right now, if we think about this conceptually, we draw our first vertex at 0, 0, 0, and then we increment x. So 0, 1, 0, 0, 2, 0, we keep incrementing. And so we can see the issue now is that we're actually drawing a plane, but it's going to go completely outside of the frame. We're only really going to see that corner. Well, what I want, okay, is for us to actually look 0, 0, 0 to sort of be the center of our terrain mesh. So in other words, we need to make sure that our terrain, right, let's draw it like how we want it. We need to make sure that the center is 0, 0, 0. So I propose that the top left coordinate be 1, 1, 0. And then the lower right coordinate is going to be what? Negative 1, negative 1, 0. This ensures that not only the terrain, that the terrain is centered at the origin, but also that since it's from negative 1 to 1, the entire sort of mesh is going to be in frame. So let's go ahead and do that. All right, so you can see what I've done is I've created this function called normalized value. And this is actually a pretty standard function that you can just find, if you look it up. Basically what it does is it takes in a value and then the current minimum and maximum of the range that value retains, and then you input the range you want to map it or assign it to. So that's exactly what we need, right? And so here's what we'll do is we'll just create a float called normalized x. So now, what should we see? Let's press F5. Let's see what happens. And there it is. That's exactly what we want. All right. So we need to take care of one more thing before we get to the fun part, where we actually start calculating noise and making all these cool terrain meshes, which is lighting. We have to take care of lighting because right now our scene is unlit. So effectively what's happening is whenever our GPU encounters a pixel that's within our mesh, it's just coloring it one color. And that's not going to do it for us because we need to be able to see like those nooks and crannies. We need to see those valleys and those rivers. But right now we're not going to see any of that. So the solution is to calculate normals. We're going to calculate normals per vertex. So I've drawn this diagram, which will hopefully help us understand what we're actually trying to do here. We're looking down the y-axis, okay? So in other words, we have the zx plane. Looking down the y-axis, zx plane. Hopefully that makes sense. And so for the normal component, the x component of the normal, we want to find the partial derivative of x with respect to z. And so in a vector calculus class, you'll learn often this technique. You'll learn to differentiate along some continuous surface. But in computer graphics world, we are not dealing with a continuous mesh. Remember, our mesh is comprised of discrete, evenly spaced positional values. Okay, so that actually makes things really simple. If we imagine, okay, this is vertex A, then B, then C. If we want to find change in x with respect to B, for instance, well then that's just going to be C minus A. It's just going to be the difference between its x adjacency to the right minus the one to the left. And actually we can do this for y as well. If you could imagine looking down the x-axis. And that is actually going to make it really simple. We can calculate the change in x and change in y, the partial derivatives of x and y, just by checking the adjacencies. And I will show you how to do that right now. So here's our code so far. There's a couple things I want to mention. First of all, we have this index variable, and we're multiplying it by 3 because, if you think about it, our vertices array for each vertex, there's 3 components. And so each vertex takes up 3 indices in that array. So if we want the current vertex for any given x and y, we have to multiply that index by 3, if that makes sense. Additionally, we have to do some checks for calculating those adjacencies because, for instance, we might be, let's say, at the leftmost vertex of our mesh, and we want to calculate the left adjacency. Well, there is no left adjacency. So instead, in those cases where there's no adjacency, we'll just substitute it with the current vertex's z component. And then we'll, as I mentioned, we'll calculate the difference between the right and left adjacency, the down minus the up, and then we'll compose a normal vector. So for the z component of that normal, you'll see I've created this variable side length, which essentially is just going to be the side length of that given cell, and that's going to be proportional to that resolution. We'll normalize the vector and then push it back. And then in our vertex shader, I'll take in those normals and then recalculate them relative to the camera space and the light source, which I'm placing 10 units above the mesh. And then I'll repurpose this fragment shader, which I got online, and we get this result. Now we can't really tell what's happening, right? Because it's still a plane. So let's add in some artificial noise. So I'm just using some Perlin noise from GLM and looking good. So for the rest of this video, I'm going to be referring to this research paper right here, which I'm going to be linking down below. I highly recommend you take a look at it. It's a very fascinating read. But for now, I just want to briefly go over the actual steps that we're going to take. So the paper outlines a sort of 2-step process. The first thing that it tells us to do is build this sort of base terrain mesh that will be uneroded. And then in step 2 is the actual erosion algorithm, which is going to take that uneroded mesh and sort of make it extremely realistic and believable. And we're actually going to be implementing this paper's main contribution, which is this idea of an optimized hydraulic erosion algorithm. So let's go ahead and get started with our base terrain mesh. So the first thing we have to talk about is this idea of 1 over f noise, or is sometimes referred to as pink noise. And essentially it's this idea where the paper says it's when the spectral energy density of an octave is proportional to the reciprocal of its frequency. Which, if you're like me, the first time I read that, I'm like, what does that mean? But it's actually not that difficult or complex. Basically, what we're talking about is a noise pattern. And the noise pattern is going to be comprised of several octaves. You don't need to know like exactly what that is. All you need to know is that each octave has a frequency and an amplitude. Okay, what does it mean for an octave to have, let's say, a high frequency? Well, that's going to correlate to a sort of steep variation in those height values over a smaller distance, which in this case is going to correlate to small features like rocks, right, boulders, things like that. And then if we have, okay, a low frequency, what does that mean? Well, it means there's going to be less variation over a longer distance. And so we can think about that as like mountains, right? Huge mountains or valleys. And so then the 1 over f noise function basically just tells us that, well, if the frequency is low, well, then there should be a high energy density or high amplitude, right? And conversely, if there's a high frequency, meaning those smaller features, then it should have a smaller amplitude. And what we'll see, as I've written here, is that that's going to yield larger features which dominate over those smaller features, which, as it turns out, is very true to how terrain actually exists. So let's go ahead and implement a simulation, or an approximation rather, of 1 over f noise called square diamond noise. Here's how square diamond noise works. We'll first start off by going to each of the 4 corners of our mesh, and we'll assign their height to a random value from 0 to 1. We'll then ask ourselves, okay, well, what is the current step size? Initially, the step size will just be initialized to the resolution, or in the side length of the mesh. Before we do the actual step, we'll divide the current step size by 2, which means that the step size for the first iteration will be half the length, half the resolution. We'll then ask ourselves, given the current points, how many unique diagonal steps can we take? Well, if you think about it, we can only take 1 to the center. Then, once we get to that point, we'll do a crucial calculation. We'll first pick a random number given some range,
and then we'll multiply it by the average of the heights of the other points that we stepped from. We'll then multiply these two values together, and we'll get that current new point's height. So that's the diamond step. Okay, so then we'll go on to the square step, which effectively says, okay, given the current step size, which to remind you is half the resolution, how many steps can we take in the cardinal directions, right? Up, down, left, right. Well, we can take 4 steps. 1, 2, 3, 4. And then we'll do the same procedure. We'll sample all of the points, in this case, the left, right, up, and down adjacency, and we'll average those points' heights and then multiply it by some random value within some range, which will give us the new height for all of those new 4 points. And then we just repeat. First we have to write divide. That's the first iteration. So then we have to write divide that step size by 2. So now we step a fourth. We'll go to there, there, and there. Again, we'll sample the points around, and you can sort of see how this goes, right? We're going to eventually exhaust all of the points in our mesh by doing these repetitive diamond steps and then square steps, and we'll see that the number of steps we take is going to increase more and more and more as we continue through the algorithm. Let's see what the actual code is. So just a quick side note before we talk about the code. I made this helper struct called a height map, which essentially allows you to take in the vertices of the mesh by reference and then resolve, given an x and y, the 1D index, and then we can either retrieve that z value at that index or we can set a new one. And we're going to see it really cleans up the code. So just wanted to talk about that real quick. Now back to our diamond noise function, you can see that I initialized a height map here, which, like I mentioned, is going to make it really easy to set those initial random values at each corner. Then I set these two variables, amplitude and persistence, which I'll actually expose to the UI. And then we'll do the square diamond noise procedure, which we're doing iteratively. Technically, you could do it recursively, but I think I often just opt for an iterative solution in this case. And so we can see we do the exact procedure I was mentioning. We do the diamond step by checking the diamond adjacencies. Then we do the square step. And then I have these two functions, our utility functions, which essentially will normalize those values inside of that array. And then we extract them. And we'll see later that extracting those z values into a new array will allow us to sort of optionally include that noise or uninclude it, depending on what the user selects. And here's our result. We can see how it closely simulates that 1/f noise that I was talking about, right? Where we have those big mountainous features which dominate over those small little divots and boulders. And it's gonna, be a really good base for the rest of our noise. I should mention, right, that I've exposed some of these variables to our UI, which is gonna be really helpful for the user. Just to give you an example, let's say I wanna change the z-scale. And by changing the z-scale, we can see, things are more drastic. Versus something that's more flat. And so you can sort of get an idea of how you can change these sliders to get a result that's more attuned to a particular environment or a particular biome, you could say. It's really just up to you to play around with. The next layer of noise that we're going to apply is called Voronoi noise, or is more commonly referred to as a Voronoi diagram. And it's an entire topic within itself that you can really dive into. But for now, I'll just outline a very simple version that is all we need for our particular use case. So the way it works, or the way we're going to do this, is by first dividing the mesh into several regions. For this example, I'll just do 4 regions like this. Okay? And then for each region, we'll calculate or we'll choose a number of feature points per region. So let's say I choose 2 feature points per region. Then comes the actual algorithm. We're going to iterate through all of the vertices of our mesh. And let's say, okay, for example, we're at this vertex, okay? All we'll do is calculate the distances between, in this case, its 2 nearest feature points. And so the z component of c in our version of the algorithm is just going to be the distance of the nearest vertex, which we'll say is a, and then we'll subtract it by the second nearest feature point. Sorry, not vertex, feature point. And that's it. For each component, for each vertex, just calculate the difference between its closest feature point and then its next closest feature point, and then find the difference. And we'll do that for each vertex. And what we'll see is that if a vertex is equidistant between 2 feature points, that its height will be 0. Thus, we get these sort of cell-like structures that Voronoi noise is known for. So then let's implement this. So here we are. Here's the implementation, and it's pretty much one-to-one to what we were talking about. You'll see I created this helper function, which will actually generate that vector of feature points so that later on we can actually iterate through those feature points per cell. I also exposed those variables, cells per axis, points per cell. I'm going to expose those to the UI so the user can modify that to their own needs. And then here's sort of the main logic of the actual algorithm, where we're constantly testing or determining whether or not the distance to the next nearest feature point is closer than the current running closest, right? If that is, then we just set that as the new closest, and then D2 as the sort of old closest. And then we just set that z component to, in this case, the difference of d1 minus d2. And you'll see if we press F5, the result we get is something like this. Let me go ahead and... So I'm mixing the square diamond with the Voronoi, but if I turn that off, then I get this result, right? And then here I'm actually doing a different variation where I do negative d1 plus d2. And I get something like that. And so now that I have the Voronois working and the square diamond working, what I'll do is I'll actually mix them together. So first I'll enable the square diamond, and we'll see that the optimal mix, according to the paper, is sort of 33% Voronoi and 66% square diamond, which you can see here is the current mixing ratio. And we get this result. Now, it's interesting, and it definitely breaks up those homogeneous features that's created by the square diamond noise. But there is a pretty obvious glaring issue, which is that we have these seams. And remember, those seams are going to be caused by points on the Voronoi diagram where the distance between a vertex from one feature point to another is the same. And so we get those seams of those vertices where the height is 0. But we can fix this, and we're going to fix it using a technique known as perturbation. All perturbation really is the act of taking something that's in some normal or fixed state and then displacing it or changing it to some altered state. And so in the context of our mesh, that just means that we take each vertex and we move it or we displace it from its original position. And so we're going to do that for each vertex. And for each vertex, we're going to carry out this 4-step process. The first thing we're actually going to do before we even iterate through our mesh is generate noise separately from our mesh, and we'll just repurpose the square diamond noise. And then from that noise, we can actually generate or pick out random directions, which will be the direction by which we displace each vertex.
So we'll pick that random direction from that noise we'll generate earlier, and then we'll displace that vertex by some percentage of the mesh size. And we can configure how far we want to displace it in the code. And then finally, once you've displaced it, we'll interpolate the value. So let's take a look at the function. So here's the function I ended up with for the perturbation. I will say that this function in particular gave me a lot of issues. There was one bug in particular that I was just racking my brain with. I was essentially sampling the mesh in place for the perturbation. So in other words, what was happening is I would encounter a vertex in the mesh, displace it, and then write back to that same mesh. And so what would happen is I would write that for each vertex and then encounter its displaced position again later on, and then end up displacing it again. So I was displacing a vertex multiple times, and it ended up creating this artifacting, which I'll put up something here to show you what I mean. And so the solution is to just copy the vertices array into another new vector. And then essentially I'm just sampling from that copied version. And that ensures that I'm sampling the positions, the original positions of the mesh for each vertex. And then I sample the diamond square noise in order to compose those random directions. And then I just displace. And we do a bilinear interpolation. I'm not really going to go into what that means, but essentially it just smooths that point in relation to the other points that are surrounding it once we displace that vertex. And then I just normalize all the values so that everything's normalized to that 0 and 1 range. Here's the mesh before applying perturbation, and then after applying it. And we can see just how effectively it breaks up those seams and really makes an excellent base terrain mesh for the next and final step of our terrain generation video, which is going to be applying the fast erosion algorithm, which is the paper's main contribution. So let's talk about it. So we've reached the final part of our project where we're going to actually be simulating erosion. And the paper really goes into a lot of detail about what erosion is, and it describes various different types of erosion, such as hydraulic erosion and thermal erosion. But to keep things simple, we're merely going to define erosion as this idea where we're moving material from steep slopes and we're depositing that material at lower inclinations. So you can imagine if we have a cliff and we have surrounding mesh that's lower, we're going to take that material and deposit it in those lower areas. And we're going to do this iteratively over and over again, just like you would imagine in the real world, where erosion continuously happens over a large period of time. And we'll see how that material sort of makes its way down to the streams, then it follows streams, it goes, it really follows those lower areas and deposits itself at the lowest point. And so we're going to do this using what we call a rotated von Neumann neighborhood. We're going to sample that neighborhood and then determine whether that cell gets eroded and where that material moves to. So I've gone ahead and drawn the rotated von Neumann neighborhood for a particular cell. I'm going to call this cell, the central cell, the current cell, or in other words, the current vertex. Here's how it works. We're going to sample all of its adjacencies, the top left, top right, bottom left, bottom right. And we're going to calculate the height differential between that current cell and those adjacencies. That's what this d sub I is. What we're going to do is we're going to keep track of the maximum differential between the current cell and all of its other cells. And we're also going to keep track of that lower cell.
So then by the time we iterate through all the cells, we'll have that maximum distance we'll call d max. And so we need to ask ourselves, given d max, should we erode the current cell? Well, let's think about this. Let's say d max is less than 0. What does that imply? Well, that implies that the current cell is lower than all of its adjacencies, which means we shouldn't erode it, right? Because remember, we should only apply erosion if the current cell has a higher inclination than those lower cells around it. We also are going to determine whether or not that d max is less than the angle talus, which we're going to define and parameterize to the user later on. If it's within that range, if it's greater than 0 and less than talus, we will erode. So here's the actual sort of crux of this entire algorithm on the right here. This is the actual erosion, where we're going to define this variable delta h, which is going to be half of that max height differential, d max. We're then going to set the height of the current cell to itself minus that delta h, and then we're going to set the height of the lowest cell in the neighborhood to its current height plus that delta h. And if we think about this, that's exactly what erosion is as we defined it. We're taking that material off of the current cell and we're depositing it to its lowest cell. And that's it. That's pretty much how it works. And we're going to do this iteratively several times throughout all of the cells in our mesh. So let's go ahead and take a look at that code. So here's the code. It's pretty much one-to-one what we were talking about. We're just going to iterate through all of the vertices in our mesh, and then for each vertex, we're going to iterate through all of those adjacencies. And we're going to use these two sort of hard-coded arrays to get those indices for those diagonal adjacencies. We'll keep track of the highest height differential between the current cell and its adjacencies, and then we'll also keep track of that lowest adjacency index, because of course later on we need to get back that cell in order to apply that material to it. And then we'll check to see if the cell is even qualified to be eroded. We'll then calculate delta, which I'm actually going to expose that ratio to the user to determine how much of that Dmax do we want to apply to that current cell and the lower cell. We'll resolve the x and y coordinates for that lower cell and the current cell, and then we'll just either add on by that amount, that material amount, or subtract. So I also wanted to show you our sort of final noise function that's going to go through each of those steps and apply all of those functions and perturbation and erosion. And you can see step 1 where we just get that base mesh with the diamond square and the Voronoi diagrams. And then here's sort of the mixing, right, where we can mix or parameterize that mix ratio. Then here's step 2 where we just apply perturbation. And then finally, here's the erosion. And you'll see I've exposed this erosion iterations variable because, of course, erosion is going to be applied multiple times. And so you're going to get different results depending on how many iterations. And we call fast erode in every iteration. So you can imagine this is a very laborious, computationally heavy algorithm. And then finally, after we've eroded everything, we should normalize the z-value. So just make sure everything's from 0 to 1. So I've started the program with erosion disabled. And if we come over here, I want to show you just the settings that I've defaulted to, which I think personally look the best, where we do 50 iterations of erosion, and then that erosion strength, right, which is the proportion of that maximum height differential. I set it to 0.25, and then the talus is going to be 4. Now, that's actually going to be proportional to the resolution. So it's really 4 divided by the side length of the mesh. And so let's enable it and see what happens. And here's our result. and we can see that it does exactly what we want it to, where it's taking that material and it's sort of moving it downwards towards those from steep areas down to those lower areas. Now you will notice there's some artifacting, and it's caused by the fact that when we sort of move that material from a lower area to a higher one, it sort of stretches out those triangles. But one way I know to make it look better is if we just increase the resolution. So I'm going to increase it. I'm going to double its resolution. It's taking a while. And then we get something like this, which I think looks pretty darn cool. So that's going to be it for this video. Obviously, I could have gone into a lot more depth on this topic. There's so much more to learn and understand, using different noise patterns, different erosion techniques, but I think I'm just going to leave it there for now. If you want, take a look at the GitHub repository. It's public. Take a look at it, and if you want, maybe build it, see if you can make some cool stuff, cool terrain patterns with it. But with that being said, like and subscribe, and I'll see you on the next one.